exponential growth differential equations, day 2. Just want to remind you of the things we covered before. We have this is our base differential equation for exponential growth, where this guy K is called a growth rate or a proportionality constant. And of course, dy by dt is the rate of change for y with respect to t. And when I have this saying that it's k times y, that's telling you that whatever y represents, that the rate of change of y is directly proportional to y itself. That's what makes it an exponential growth differential equation. A couple things we did last time that I like to do again a little bit quicker now is we're going to solve the differential equation. It's a first order separable differential equation, so we can separate and integrate. Obviously this y needs to come over here, dt needs to go over there, k is simply a constant. So when we separate, it'll be dy over y equals k dt. And so we separate and then we integrate. And so we integrate and we'll have ln y is kt plus some constant. Of course, the variable of integration here is t, and so when I integrate a constant, I get the variable of integration, so I have the kt. And then if we were to solve it, we would make these exponents of e, and you have e to the ln y equals e to the power of kt plus c. Of course, e ln y is y. E to the kt plus c could be thought of as e to the kt times e to the power of c. And e to the power of c is just another constant, so you can call it c. And so our final solution would be c times e to the power of kt. So this is the exponential growth differential equation. This is its solution. Now, what was also mentioned the other day is, again, in this solution, I have these different variables, and so the only true variables are y and t. They're varying. E, of course, is a constant. K is a constant. It's the proportionality constant. And c is also a constant. But if you look at the initial value, so say I take the value of y when t is 0, which we call the initial value. In fact, I'll call it the initial value. I won't even use a variable. I'll use a whole word. If I was to apply this initial condition to this equation, meaning I'm plugging in 0 for t and initial value for y, what I would get is this y would turn into initial value, and c, e, t would turn into 0. And so I would have my initial value is c times e to the power of k times 0. K times 0 is 0. E to the power of 0 is 1. C times 1 is c. And so you can see that c is the initial value. So we have these exponential growth differential equations. This guy c in the solution is the initial value, or sometimes called the initial population, because these are used a lot of times for populations. So next, I want to go through a couple of examples. So I'm going to do 4 examples. The first 2 I did in the previous video, but I just kind of refreshed myself on those. And the last 2 are going to be new. All right, so I'm going to go ahead and put the problems on the screen. Okay, so you saw the problem on the screen, and the problem said if dy by dt is 7y, and y is 3 when t is 0, what's y? So once we find y as the solution, what's the solution? Now we know y takes the form, so y is going to look like this. C e to the power of kt. That's how y is going to look. Now again, in this solution, y is going to stay y, t is going to stay t. Those are guys that are very independent on the situation. E is also going to stay e. E is a well-known constant. And so we have to find the values of c and k. We have to find the values of c and k. Now in this very simplistic example, c and k are looking at us straight in the eye. So we know that the generic form of an exponential growth differential equation is that dy by dt equals ky. So obviously k is going to be 7. That's fairly straightforward. K is 7. So I found k. The other thing I need to do is find c. If you recall, c is the initial value. The initial value is the value of y when t is 0. Well, it says y is 3 when t is 0. So obviously c is 3. So this answer to the problem is y equals 3e to the power of 7t. So that was a pretty simple example, very vanilla. And so I add some fudge and some different type of pecans and other type of nuts and caramel a little bit later. Now I'm going to put on the screen the second example, which was also covered in the previous video. All right, so you just see the second example, and in the second example, let's say you have something of the form of dy by dt equals ky, and the population doubles every 5 years, and it wants you to find the value of k. Again, we did this in a previous problem, and again, when we measure populations, what we find is typically pretty important to determine how long it takes a population to double, particularly things that rise exponentially. And so again, if you've been watching the news about the COVID-19, you always hear them say about the time it takes the number of cases to double. And as we go a little bit deeper into this, you'll kind of understand the math behind how infectious diseases increase. Is something called the SIR model, which we'll look at a little bit later when you get a better understanding. All right, so for this problem, however, so I want to find the value of k. I know the solution to this differential equation is y equals ce to the power of kt. I know that c is the initial value. So I know that when t is 0, y equals c. This I know by definition. Now, every 5 years, the population is going to double. So that means when t is 5, my population should go from c to 2c. So when t is 5, y should be 2c. So I'm going to use this information to solve for k. So again, I'm going to plug this number in for t. I'm going to plug this value in for y, and then I'm going to solve for k. So if I plug it in, so y becomes 2c, and this is c, e, and t is 5, so 5, k. So there's my little equation. It's just a little exponential equation. We saw things like this in pre-cal all the time. You can notice I can divide both sides by c. And where I get 2 is e to the power of 5k. course, to solve for k, there's two ways you can think of this. You can ln both sides, or you can just write it in logarithm form. That's how you solve an exponential equation. I'll think of it as putting ln to both sides. So this would be ln 2 equals ln e to the power of 5k. ln 2 is some number. We'll figure out what it is in a second. ln e to the 5k is just 5k. So what we have is 5k equals ln 2, which means k is ln 2 divided by 5. So that's a calculation I need to do in a calculator. However, prior for me doing that calculation, I'd like to point out something about k in this type of scenario. So k is ln 2 divided by 5. So whenever we have a doubling problem, so a doubling exponential growth differential equation, and it wants you to find k and it tells you the population doubles after so many years, it will always be ln 2 divided by the number of years that it takes the population to double. And again, we commonly use double for populations, but if it said triple, we would do ln 3 divided by the number of years it takes the population to triple. If it said quadruple, we would do ln 4 divided by the number of years it takes the population to quadruple, and so forth and so on. So again, I'll do this little calculation in the calculator. I have a handy calculator here, and what I'm going to do is I'm going to go ln 2 divided by 5, so about 0.131. Alright, so that's how you do that particular problem. I'll now go ahead and put the third example on the screen. Alright, so the next problem, I put the problem on the screen, and so I just want to read it. And so I have it on my phone, and that's why I need these glasses. So it says a bacteria has a population of 8.3 million at time t equals 0. And so that's why I have y of 0 equals 8.3, and a population of 11.3 million at time t equals 5. And that's why I have y of 5 equals 11.3. If the bacteria's population is increasing according to the laws of exponential growth, what will be the population at time t equals 9? So the population is increasing due to the laws of exponential growth. That means that the growth of the population can be modeled by dy dt equals ky. And if this is the model, that means the solution of this model is y equals c times e to the power of kt. Now I want to solve for y9, so I want to plug in 9 for t and solve the equation. In order to do so, I need to know the values of c and k. I need to know the values of c and k. Now, again, c is the initial condition, it's the value of the population when t is 0. That is given to us. Y of 0 is 8.3, so c is 8.3. Alright, so we found c fairly easy. Now we need to find k, and then we'll just plug in 9 for t and be on our way. So to find k, I'm going to need to use this second condition that was given. So in order to find k, I'm going to plug in 5 for t, 11.3 for y, and then I'll be able to easily solve for k. So y is going to become 11.3, 8.3 e to the power, and t is going to become 5, 5k. So we'll solve for k like that. Again, to solve this exponential, you want to get rid of the coefficient of e, so you divide both sides by 8.3, and you have 11.3 divided by 8.3 is e to the power of 5k. And so again, that's an exponential that's solved by a natural logarithm, ln. You've seen it several times, so I'm going to do it fairly quickly. And that means that 5k is going to be ln 11.3 over 8.3. So 11.3 over 8.3 is a positive number, and so I'm allowed to put it in parentheses versus an absolute value sign. And so, of course, k is going to be this number divided by 5, obviously. So k is ln 11.3 over 8.3 divided by 5. And so that's a calculation one needs to do in a calculator, and so I'll do it. And so when I do the calculation, I get k is approximately 0.062. 0.062. And so we generally round to 3 decimal places for most of our values. Okay, so I know the value of k. So plug in the value of k into this guy. So y is going to be 8.3 e 0.062 t. So there's the solution to the differential equation with the value of c and k plugged in. So now to find y of 9, just going to plug in 9 for t. So this is 8.3 e to the power of 0.062 times 9. And so that's a calculation you would need to do in a calculator, and I couldn't do a complex calculation like this, but I believe the answer is 14.5. All right, and now I'm going to put the last example on the board, on the screen. All right, so you see the last example. This is a pretty good example. On this problem, so I'm just reading the problem. It says the weight of a population of yeast is given by the differential function y, where y of t is measured in grams and t is measured in days. The weight of the yeast population increases according to the equation dy by dt equals ky, where k is a constant. At time t equals 0, the weight of the yeast population is 120 grams. So that's why I have y of 0 is 120, but also and is increasing at a rate of 24 grams per day. So the weight of the yeast is increasing at a rate of 24 grams per day. That's a rate. So that refers to dy by dt. So dy by dt equals 24 when t is 0. So these two statements were both occurring when t was 0. And so they just want me to find the solution to this differential equation is essentially what they're asking for. I know the solution is going to be able to form y equals c e to the power of kt. Now again, typically what I need to find are c and k. C is the value when t equals 0, so c is 120. So y equals 120 e to the power of kt. Now to solve for k, I'm going to use this condition. To solve for k, I'm going to use this condition. But notice this condition is dealing with dy by dt. So I'm not going to use this condition on this guy. Notice there's also a k in this guy. So sometimes I can solve for k using this guy. As long as I have the rate and a value for y, I can solve for k using this, the differential. Now you may say, well, you don't have a value for y here. This is saying the rate dy by dt is 24 when t is 0. That's true, but I also know that when t is 0, the value of y is 120. So I do know the value of y when t is 0. So using this condition in conjunction with this condition, that means that dy by dt is 24. Again, this is when t is 0. And y is 120. So I should write that as 120k. So here I can easily solve for k, of course, by dividing by 120. And so if I divide both sides by 120, 24 over 120, 24 goes to 125 times, so k would be 1 over 5. So for my final answer, I just need to plug in 1 over 5 for k. So the final answer would be y equals 120 e to the power of, let's say, since k is 1 over 5, t over 5. We also could have put 1 over 5t. Alright, that's going to conclude our Day 2 Exponential Growth Differential Equations lessons. I've put now 4 different types of problems, and you will see those 4 different types of problems on your next assignment.